In the previous chapters, we had learned about Newton's laws, and we applied Newton's laws to a variety of problems to help describe the forces acting on the object and then explain how things would move, for example. Let me give you an example. You studied the inclined plane problem, like a block that was on an inclined plane. We studied the forces acting on it, which was the force of gravity and the normal force. And then applying Newton's second law, sum of F equals ma, you could determine, say, the acceleration of the object. And then if you knew the acceleration of the object, then you could use kinematics and figure out, for example, the speed when it reaches the bottom. Well, it turns out that this is not necessarily the easiest way of solving this kind of problem. In fact, there's a much easier way using conservation laws. A conservation law is basically a physical law where quantity remains constant. It doesn't change with time. Now, there are a variety of conservation laws that you'll come to see in this course. We'll see conservation of mass, conservation of electric charge, conservation of momentum, and so forth. Right now, we're going to be studying the conservation of energy, which is essentially that the total energy of an isolated system, or the universe, remains constant through time when certain physical processes occur. So energy cannot be created nor destroyed. It can be transferred or transformed from one form into another. But the total energy of the system remains the same. So when we write E sub I equals E sub F, you're essentially saying that total energy initially is equal to the total energy afterwards, and you're assuming the physical law of conservation of energy. The concept of energy will appear throughout this entire course, and it's not easy to define what energy is. There's a lot of different types of energy. You can have kinetic energy, elastic potential energy, gravitational potential energy, rotational kinetic energy, and so forth as the list goes down. Now, in this chapter, we're going to be concerned with only mechanical energy. Mechanical energy is the energy that's associated with the motion and the position and the deformation of objects. Essentially, it's going to be these first three energies that are listed here. So we're going to be looking at kinetic energy. So kinetic energy is energy that is associated with the motion of an object. In fact, you calculate the kinetic energy of an object by just using 1/2 times the mass times the speed squared. So if an object with mass m is moving, then you've got kinetic energy. Now there is a different type of kinetic energy as well called rotational kinetic energy. This is when you have an object that is rotating, spinning. We won't be studying this in this course. It's not part of the AP Physics B curriculum. So we're only going to be looking at translational kinetic energy. Now there is another class of mechanical energy which does not relate to the motion of an object. It has to relate to what we call stored energy. So potential energy, sometimes I abbreviate that with a PE as potential energy, is a stored energy. Now there are two different types of potential energy that you'll come to see in this chapter. We have elastic potential energy. Let's say you stretch a sling and you pull back with it with more and more force, and eventually it stretches here, and then you release an object, and then eventually it turns into a different type of energy. Well, when you stretch this object, you're storing what we call elastic potential energy. Any object that has some kind of springiness to it, like a spring that can be compressed or stretched, or a sling that can be stretched, or a bungee cord, anything that can be basically deformed in some way, then you have what we call elastic potential energy. Now there's another type of stored potential energy, and that is the energy that is associated to moving an object to a sort of elevated position. If you take a look at the example down below here, we have that rock being pulled back in a sling, so we're storing elastic potential energy, then we release the rock, eventually goes really fast, and so we have kinetic energy, and then as the rock rises, it's losing kinetic energy, it must be gaining some other type of energy, and that would be called gravitational potential energy. So that is energy that is stored in the gravitational field So when an object changes its location in the gravitational field, we have what is known as changes in gravitational potential energy. So that is another formula that you'll see later on as delta U. U is the symbol we use for potential energy, by the way, with little subscript g for gravitational potential energy, and this is equivalent to mgh. There's also you'll see this formula for the spring objects. It's 1/2 kx squared. Anyway, I'm not going to really get into the formulas at this point in time because you'll be introduced to them more formally later on. What I want to get at is just to give you an idea that we have kinetic energy and these two types of stored potential energy, which make up what we call mechanical energy. And these energies can be converted from one form into another, as you saw in the example below, and they could even be transformed or transferred from one place to another, but the total amount of energy before and the total energy afterwards of the isolated system remains constant. Now, because energy is kind of hard to define and sometimes people struggle to understand conservation of energy, I sometimes like to use an analogy to help you understand. I like to talk about money, because we all understand money. Let's say you have a job on the weekends, you work, and eventually you're going to get a paycheck at the end of the month. And that paycheck may come in the form of bills or coins, or even a paycheck, or maybe it's directly deposited into your bank account. You see, money is very similar to energy because money comes in many different forms. It can come in all these different forms. Just like energy can be kinetic energy or gravitational potential energy or elastic potential energy or even nuclear energy or chemically stored energy. So there are all these variety of forms of energy, and kind of money's like that too. And you can also transform energy, right? And hence you could also do that with money too. You could, for example, go to the bank and cash your check and turn it into, say, bills. Or you could change your bills into coins. So there's a variety of ways that you could transform, or you could even transfer it to other people, right? So these transfers and transformations do not change the total amount of money that you have. So money can be stored in your bank account, so that's like potential energy, or it could be spent, so that's kind of like kinetic energy. But one could say that money is not always exactly like energy. For example, you could destroy money. You can't destroy energy. You could create money. Governments do that, right? You can't create energy. So energy cannot be created nor destroyed. Otherwise, it would be violating the law of conservation of energy that is listed above.